In this video, we're looking at exponential functions. Specifically, we'll define them, transform them, solve some questions involving them, and also look at one exponential function or expression that involves something called the number e. To begin with, an exponential function is one in which the variable, one of the variables, is in the exponent. If you look at the list of all the functions that we've seen, or ones that we will this semester, none of them are exponential functions. Linear, x is down, where you can get at it, where you can get at it, where you can get at it. Same with all these. Only exponential do you have an x that's in the exponent. We'll talk about logarithms as well, and they're related, but none of the other ones, including trig, have a variable that's in the exponent. And those are exponential functions, and they're characterized by graphs that look like that. And you've seen some of those before. Specifically, our pandemic with COVID, the number of cases has increased exponentially. Okay, so take a look at these. Your turn for a second, and just in your mind, I'll move them, but in your mind, determine which of those are exponential and which aren't. Put the green one, the exponential ones in the green box and the others in the other. Okay, looking at this one, yes, I've got an exponent, but it's not a variable that's in the exponent, so it's not exponential function. This one has an exponent, which is a variable. So does that one. This one, it's not an x in the exponent, but it's still a variable. It's a number that we can solve for. So that's exponential. This one has an exponent, but the exponent isn't a variable, so it's not exponential. Okay, let's look at transformations of exponential functions. We've already looked at that in the last section on transformations, but I wanted to do it specifically with exponential function. Some people get the a mixed up with whatever the base is. So this number here can change. So right now it's 2, it could be a half, it could be 10, whatever. But that's just sort of part of the normal function. It's not part of the transformation. It does change the shape of the graph slightly, but it's not one of the 4 transformations that we looked at. So there could be a number out front in the exponent. There could be a number or a letter there, number there, and 1 at the end. As you recall from before, that affects the vertical stretching, and it also reflects the graph over the x-axis. B is the horizontal stretching or squishing. It also allows things to flip over the y-axis. C moves things left or right. D moves things up or down. So let's just try one. So if you have decimals open, fire it up and maybe put in a function. Let's put the base function in first. Let's use a 2. Doesn't matter. We'll be 2, and then you hit that A, B button to get an exponent of your choosing, and let's put an x up there. So there's a beautiful exponential function right there. But then let's go down to another place and let's put in another one. So let's maybe put a number out front. Let's put like 10 out front. So 10 times 2 to the power of x. Okay? And so what's happening there is that every y value of the red function is being times by 10. And that's why there's a vertical stretching that's happening with that. Okay, yeah, let's maybe leave that on there. Let's do another one. Y equals, let's go 2 to the x, put our x up there. And maybe let's put a takeaway 1 up there. Oh, that's one thing you have to remember. If you want to put something up in the exponent, you have to put bracket. So I'm going to put bracket there, then I'm going to put x, say minus 3. Minus 3 bracket. Okay, so let me get rid of this blue one. So the red one is the normal one, and you take a look at the green one, and notice that it's moved over 3 to the right, just sort of like what we knew from the last time. While we're on that one, let's maybe put a d value in too. Let's move it, say, up 2. So I'm going to put a plus 2 there at the end. Sure enough, it takes that same graph, moves it over to the right 3, and moves it up 2. Okay, let's maybe, let's hide this one. And let's take our first one. And what I'm going to do is I'm just going to put a negative number in the front. Y is equal to negative 2 to the x. See how that does exactly, hopefully, what you thought. The negative out front in the A spot, it reflects things on the x-axis. Why don't we try and put, instead of doing that minus there, let's get rid of that. Let's put minus up there with the x value, if I can get up there. Let's put a minus sign right there. Oh, so that one, I guess, does exactly what we thought. It's going to reflect it over the y-axis. This is getting fun. Why don't we put a minus in both of them? I'm going to put a minus right there. See what you think it's going to do. And then press play and see if you're right. Hopefully you were right. So that one reflects it over the x, and it reflects it over the y. And so those values A, B, C, and D do the same thing that we saw with every other function. Try that one. Maybe just look at it and see if you can determine what's going to happen to it. Press pause and then play. So I would start up here in the bracket. The plus 3 there tells me that it's going to move left 3. And then the minus tells me it's going to reflect over the y-axis. And the minus 1 means it's going to go down 1. So I've plotted the normal y equals 2 to the x graph there. So this one's going to move to the left 3. So an easy way to tell it to move to the left 3 is just pick any point, and I use the y-intercept right there, and go over 3. 1, 2, 3. So that same spot on the graph has to be right there. So instead of coming up later, this one's coming up earlier. You could figure out what the y-intercept is, but we've got more transformations to do on this one. So suffice to say that it got moved over 3 to the left so far. Then this minus sign means reflect it on the y-axis. That's this one. So let me use a different color. Let's go blue. So instead of going up that way, it's going to come up this way. So I'm trying to mirror that on this y-axis. Okay, looking beautiful. And then I have to move it down 1. So take that green graph and move it down 1. So it's going to look something like that. Something like that. And if you want, and in the book I think that they tell you to try this, is to plug in some numbers. Like I was going to do that y-intercept. So what I could do is I could plug in a 0 to determine the y-intercept, or to determine the value of the function when x is 0, and then solve that. 0 plus 3 is 3, so it'll be 2 to the negative 3, take away 1. 2 to the negative 3, if you do that on your calculator, I think it's 0.125. So you get 0.125 minus 1 would be 0.875 to the negative. And so you could actually figure out exactly, your point would be 0 and negative 0.875. And so you could find a spot that would probably be right about there on your graph. And so my graph is a little bit out. Hopefully you get the idea of doing those transformations with exponential functions. A good example of an exponential function, and one that is used frequently, is that of the compound interest formula. This is the one that says if you put money in the bank, certain amount of interest rate, how much money are you going to have at the end? And so this formula here, and it's probably similar ones you might have seen before for exponential functions, where A stands for your amount of money at the end. So what's the total amount of money? P is your principal, and that's how much money you're starting with. R stands for your interest rate, whatever your percent interest is. And make sure when you type in the rate that you don't express it as a percent, express it as a decimal. Okay, so no percents, express it as a decimal. So for example, 5% would be the same as 0.05. We always divide this number by 100. And then N stands for the number of compounding periods. So how often are they giving you money every year? Typically, the accounts you get now are compounded yearly, um, but sometimes you get things that are compounded more frequently. Sort of like your MasterCard or Visa. If you don't pay your card at the end of the month, then the next month they charge you how much money you borrowed or you used to buy stuff, and they charge you interest on the interest. So every month they charge you interest on the interest. Okay, so N up here is the same thing. So you have to use that number twice. And then T stands for the time. Or in this case, typically it's a number of years. Let's try a question. So we've got 1,500 bucks that we want to put into an account. It's going to pay us 4% compounded quarterly. So that means 4 times a year. So how much money I'm going to have after 10 years? So let's plug things in. A is equal to principal, 1,500 bucks, 1 plus the interest rate, 4%, so it's 0.04 over N, the number of compounding periods per year. This is quarterly, so it's 4, all to the NT. So N is 4 times the time is 10. Okay, so you can do this in decimals. I'll pull up decimals and just sort of show you how to do that. You can use a calculator too, but I like decimals. Okay, I did that in decimals. It's very small, probably barely see it. Anyway, I like in decimals how it looks exactly like I've done it. Maybe I'll make it bigger there for you to see. So it looks exactly like I have it there. Okay, so that's equal to 1,500 bucks, 4%, 10 years. After 10 years, you're going to have 2,233. Let's do the cents, 295. So I call that 30 cents. 2,233.30. Okay, you try one. Your grandparents 20 years ago started a fund for you. They put 2,000 bucks in. If you're getting an average rate of return of 7%, which is real high, how much money are you going to have now? You try it and then press play and see how you do. That's a lot of money. So I did that. Sorry, doing a video, Donna. So that's a lot of money. So started with 2,000 bucks, you wind up with almost 8,000 bucks. I'll just write that down. So, and you can see how I did it right there, right? So 7,918.52. That's how much money you'd have in the end. Okay, now would be a good time to talk about the number E. The number E is an irrational number. It's similar to pi. You've played with pi before, and pi is a relationship between the circumference and the diameter of a circle. If you divide those two, you always get the number 3.1415926, etc., and it never repeats. Well, the number E is a similar number. It's irrational. So the number is 2.71828, etc., and it never starts repeating. What the number E is, it's a number or a relationship that occurs naturally in any situation where a quantity increases at a rate proportional to its value. So a good example is be a bank account. You put money into a bank account, and if you make interest on the interest, then a relationship that happens there is the number E. Okay. Another example is if you look at a population of people, you don't just get new people appearing from anywhere, they appear a result of the current population. So a relationship that happens as that population increases or decreases would be the number E. Here's a good example. Okay, here's a good example of a function where they're using the number E. So you take some medication, and over time, the amount of that medication in your blood decreases. And it decreases at an exponential value or way according to this function here. So M of t is how much um, you have in your blood at a specific time. T is the time elapsed since you took the medication. So this question says, how much medication is left in your blood after 4 hours? So I can figure out, so the amount of medication after, I can put a 4 in there, is equal to 20 times e to the negative 0.8 times 4. Okay, now just plug that into your calculator and see what you come up to. I'll just do that in decimals and see how it comes out there. Okay, let me make that, I'll just put that right there. In decimals, you don't have to type out a function. You can actually just write out some numbers too. So if you want to go 20, whoops, 20 times E, you get that from the number thing, so E with a letter thing, to the, that's that A, B button, and then you have to put this in brackets. So negative 0.8 times 4, times 4. And your bracket. So right down there, it shows you how much. So 0.815. So the amount of medication you have after 4 hours is 0.815 milligrams. Okay, that's a good example. Here's another example that you can try on the next page. Okay, try this one. Press pause and then come back. Okay, hopefully you're back. With this question, hopefully you got a little frustrated. Because there's a problem because we don't have a tool to solve it. Let me just plug stuff in. It says you have 1 milligram left in your blood, so this number here is 1, is equal to 20 times e to the negative 0.8 t. Our problem is we don't have any tool, unless you've taken exponents and logs, that I can use to get at that t. Some of you maybe have tried like a square root or something, but there's no tool that we've learned so far, unless you've done exponents and logs, that are able to get you to that t. Like you can't divide by e to get rid of that because this isn't an exponent. So you can't use that tool here. I guess what you could have done, like in that last question, they said how much is left in your blood after 4 hours. You could have gone to 4 and read up at that point right there and gone off to the side and said, well, that's maybe about 1 milligram, maybe just a little bit less. And it turns out that that's what the answer was, just a little bit less than 1. With this one, we could do the same thing. So we could read up at 1 here and then go across and find where where that hits the red line and come down. In this one, it looks like it's very close to 4, somewhere just above or just below. Maybe I should erase and just actually see. Oops. So if you look at the 1, it looks like it's, when it hits 1, is just a little bit before, right about there. So just a little bit before. So just under 4 hours, you'd have 1 milligram of medication left in your blood.